Welcome back to Python DSA. In this video, we are doing a deep dive into one of the most fundamental data structures in computer science, the linked list. We will go from the absolute basics all the way to the classic interview problems you will see at top tech companies. Let's get into it. So what exactly is a linked list? A linked list is a linear data structure, just like an array, but with one key difference. The elements, which we call nodes, are stored in non-contiguous memory locations. Instead of sitting right next to each other in memory, each node can be anywhere on the heap. What connects them are pointers. Click each node in a linked list carries two things. First, the data, whatever value you want to store. Second, a pointer, a reference to the next node in the sequence. Click. The entire list is accessed through a single entry point called the head pointer. The head points to the first node. Every node after that points to the next, forming a chain. And the last node, its pointer is set to none, which in Python means there is nothing after me. Look at the diagram on the right. Head points to node 10, node 10 points to node 20, node 20 points to node 30, and node 30 points to none. Simple, clean, and very powerful. Before we write any code, let's understand why linked lists exist. The comparison with arrays tells the whole story. Memory. Arrays require contiguous memory. Every element must be right next to the previous one. Linked lists don't care. Each node can live anywhere in memory. Access. Because of that layout, arrays give you O1 random access. You can jump directly to index 5 in constant time. Linked lists require ON sequential traversal. You have to walk the chain node by node. Insertion at the head. This is where linked lists shine. Inserting at the front of an array requires shifting every existing element one step to the right. That's ON. In a linked list, you just create a new node and update the head pointer. Constant time, O1. Deletion at the head. Same story. ON for arrays, O1 for linked lists. Memory overhead. Arrays are lean, just raw data. Linked lists pay a price. Each node carries one extra pointer. Doubly linked lists carry two. Cache performance. Arrays are cache-friendly because their elements are contiguous. Linked lists scatter nodes across memory, which can cause cache misses and hurt performance in practice. Click the rule of thumb is this. If you need fast random access, use an array. If you need frequent insertions and deletions, especially at the front, a linked list is your friend. Next, there are three main variants of linked lists, and each has its own use case. Click singly linked list. The simplest form. Each node points only forward to the next node. You can traverse from head to tail, but you can't go backwards. Simple and memory efficient. Great for stacks and queues. Click doubly linked list. Each node has two pointers, one pointing forward to the next node, and one pointing backward to the previous node. This enables reverse traversal and makes tail deletion O1. Python's collections.dq is implemented as a doubly linked list under the hood. Click circular linked list. In this variant, the last node doesn't point to none. It points back to the head, forming a closed loop. This is ideal for round-robin scheduling, carousel UIs, or any problem where you need to cycle through elements continuously. We'll see code for all three types throughout this video. Everything in a linked list starts with the node class, the fundamental building block. Click for a singly linked list. Our node is dead simple. In __init__, we store the data and set self.next to none. That's it. Two attributes. Click for a doubly linked list. We add one more attribute, self, previous, that points back to the previous node. Click. Now let's create some nodes manually to see how the chain is built. We create n1 equals node 10, n2 equals node 20, n3 equals node 30. Right now they are three isolated nodes floating in memory. To link them together, we set n1.next equals n2, and n2.next equals n3. Now n1's next pointer points to n2, and n2's next pointer points to n3. n3's next is still none. It's our tail. We now have n1 right pointing arrow n2, right pointing arrow n3, right pointing arrow none. Notice how none in Python plays the role of a null pointer. It signals the end of the list. Now let's wrap our nodes in a proper linked list class. Click. The constructor simply initializes self.head equals none. An empty list has no nodes yet. Click is underscore. Empty is a convenience method. It returns true if head is none. Click __len__, gives us the length via Python's built-in len. We walk the list, counting nodes, and return the total. It's ON. We have to visit every node. Click __repr__. is for pretty printing. We collect every node's data into a list, join them with right-pointing arrows, and append right-pointing arrow none at the end. Now we can just print LL and get a readable output like 10 right-pointing arrow 20, right-pointing arrow 30, right-pointing arrow none. These helpers will serve us throughout the rest of the code. Think of them as the scaffolding on which will hang all the real operations. Ext. Traversal is the most fundamental operation, visiting every node exactly once. Click the traverse method is a while loop. We start at self.head, print the current node's data, then advance current to current.next. We keep going until current becomes none, which signals we've passed the last node. On time, O1 space. Search works similarly, but instead of printing, we check whether the current node's data equals our target. If we find it, return true. If we exhaust the list, return false. Click look at the trace on the right for a list. 10 right-pointing arrow 20, right-pointing arrow 30. We start at node 10, print 10, move to node 20, print 20, move to node 30, print 30, move to none, and stop. Output 102030. One important rule: never lose track of the head pointer. If you accidentally overwrite self.head during traversal, your entire list becomes unreachable. Always use a separate current variable as your walking pointer, and leave head untouched. Let's talk about insertions. We'll cover 3 positions: the head, the tail, and an arbitrary position. Head insertion is the jewel of linked lists. It runs in O1, constant time regardless of list size. Click Step 1. Create a new node. Click Step 2. Point the new node's next at the current head so it becomes the predecessor of the old first node. Click Step 3. Update self.head to point at the new node. Done. Click look at the demonstration. We start with an empty list. Insert 30. List is 30 right-pointing arrow, none. Insert 20 at head, 20 right-pointing arrow, 30 right-pointing arrow, none. Insert 10 at head, 10 right-pointing arrow, 20 right-pointing arrow, 30 right-pointing arrow, none. Click the diagram makes it visual. The node is new, highlighted in green. We wired its next to the old head, 20, then redirected head to hidden. The rest of the list stayed completely untouched. The callout says it all. Head insertion is always O1. No matter how long the list is, you only rewire 2 pointers. Ext. Tail insertion appending to the end is ON in the basic version, because we have to walk the entire list to find the last node. Click edge case first. If the list is empty, just set self.head to the new node and return. Click otherwise. Walk current forward until current.next is none. That's our last node. Click then set current.next equals new underscore node. The new node is now attached at the end. Click look at the demo. Insert 10, 20, 30 in sequence, and we get 10 right-pointing arrow 20, right-pointing arrow 30, right-pointing arrow none. Click, but here's the optimization. Keep a tail pointer as a second attribute on the class. Now insert underscore at underscore tail becomes O1. We skip the traversal entirely. Self.tail.next equals new underscore node attaches at the end, and we update self.tail to point to the new node. For any production linked list that does a lot of appending, always carry a tail pointer. Sometimes you need to insert at an arbitrary index, position-based insertion. Click first. Handle the case where POS equals 0. That's just a head insertion, so we delegate. Click for any other position. We walk POS 1 steps from the head to land on the node just before the insertion point. We check at each step whether current has gone to none. If so, the position is out of bounds, and we raise an index error. Click once we're at the right spot, we rewire 2 pointers. The new node's next equals current.next, and current.next equals new node. This splices the new node in between current and whatever came after it. Click the demo shows inserting 30 at position 2 into 10 right-pointing arrow 20, right-pointing arrow 40, right-pointing arrow 50. We walk to index 1, node 20, wire the new node 30 between 20 and 40. Result: 10 right-pointing arrow 20, right-pointing arrow 30, right-pointing arrow 40, right-pointing arrow 50. The order of those 2 pointer assignments matters. Reassign new underscore node.next first, then current.next. Do it the other way, and you lose the rest of the list. Ext. Now let's handle deletion. We'll delete by value. Remove the first node whose data matches a given target. Click edge case. If the list is empty, it's an error. Click special case. If the head node itself holds the target value, advance self.head to self.head.next. The old head becomes unreachable. Python's garbage collector will clean it up automatically. Click for values in the middle or at the tail. We need 2 pointers, previous and current, both starting at head. We walk forward until we find the target value. Click when found. We execute previous next equals current.next. This bypasses the target node entirely. The pointer chain now skips over it. Click if we exhaust the loop without finding the value, we raise a value error. The demo, starting with 10 right pointing arrow 20, right pointing arrow 30, right pointing arrow 40, delete 20. Result, 10 right pointing arrow 30, right pointing arrow 40, right pointing arrow none. Node 20 is gone, and no shifting was needed, just one pointer update. Let's visualize exactly what happens when we delete node 20 from 10 right pointing arrow 20, right pointing arrow 30, right pointing arrow 40. Click Step 1. We advance current until it points to node 20, the target. Previous is trailing one step behind, pointing at node 10. At this moment, the link 10 right pointing arrow 20 still exists. Click Step 2. We execute previous next equals current.next, which means 10.next equals 30. Look at the after diagram. Node 20 is completely gone. The chain now reads 10 right pointing arrow 30, right pointing arrow 40, right pointing arrow none. Node 20 still exists in memory for a brief moment, but because nothing in the program holds a reference to it, Python's garbage collector will reclaim that memory automatically. You don't have to manually free anything. That's one of the great benefits of a managed language like Python. Click That's the power of pointer manipulation. One line of code, previous next equals current.next, and an element physically disappears from the data structure. Reversing a linked list in place is a classic interview question, and the solution is elegant once you internalize the three-pointer pattern. Click. We initialize 2 pointers. Previous equals none, and current equals self.head. Click inside the loop. We do 3 things on every iteration. First, save the next node before we destroy the reference. Next underscore node equals current.next. Second, reverse the link. Current.next equals previous. Third, advance both pointers. Previous equals current, current equals next underscore node. After the loop, current is none, and previous is sitting at the old tail, which is now the new head. Click line 12, self.head equals previous completes the reversal. Click the demo and diagram tell the full story. Before, 1 right pointing arrow 2, right pointing arrow 3, right pointing arrow 4, right pointing arrow 5, right pointing arrow none, with head at 1. After, 5, right pointing arrow 4, right pointing arrow 3, right pointing arrow 2, right pointing arrow 1, right pointing arrow none, with head at 5. All done in a single pass, on time, 0 extra memory 01, space. The key insight is that on every iteration, you're pointing 1 arrow backwards. After n iterations, every arrow in the chain has been flipped. Next. A doubly linked list extends each node with a previous pointer in addition to next. This bidirectional linkage unlocks some very useful O1 operations that a singly linked list simply cannot do. Click the class holds both a head and a tail pointer for O1 access at both ends. Click insert underscore at underscore head. If the list is empty, both head and tail point to the new node. Otherwise, wire node.next to the current head, update the old head's previous back to the new node, then move self.head forward. 2 extra pointer assignments compared to singly LL. Click insert underscore at underscore tail mirrors this logic. Wire the new node's previous to the current tail. Update self.tail.next to the new node, then advance self.tail. Click delete underscore tail is the real showcase. In a singly linked list, deleting the tail requires a full ON traversal to find the second to last node. In a doubly linked list, we jump straight to self.tail. Previous, that is the second to last node. 1 pointer update, self.tail equals self.tail, previous, then self.tail.next equals none. Constant time, 01. Next. With a doubly linked list, traversal becomes bidirectional. Click traverse underscore forward, starts at self.head, and follows next pointers. Same as a singly linked list. Click traverse underscore backwards starts at self.tail, and follows previous pointers, working backwards through the chain. Click the demo inserts 10, 20, 30, 40. Forward gives us 10 left right arrow 20, left right arrow 30, left right arrow 40, left right arrow none. Backward gives 40, left right arrow 30, left right arrow 20, left right arrow 10, left right arrow none. The callout note driving this home, the previous pointer, is exactly what makes O1 tail deletion possible. No traversal needed. If you ever need O1 operations at both ends, a doubly linked list with head and tail pointers is your answer. And in Python, collections.dequay gives you this out of the box. Next. In a circular linked list, the last node's next doesn't point to none. It wraps around back to the head, forming a continuous loop with no definitive end. Click the insert method handles 2 cases. If the list is empty, the new node is set as head, and its next points to itself, a loop of 1. Otherwise, we walk to the last node, the one whose next equals the head, attach the new node there, and set the new node's next back to the head, closing the circle again. Click traverse is a while. True loop. We print each node's data and advance, and we stop when cur loops back to self.head. Important, you would never use while cur. Here the way you do in a singly linked list, cur will never become none. Always use the back to head sentinel as your stopping condition, or you'll infinite loop. Click the demo inserts 1 to 4, and traverse prints 1 right pointing arrow, 2 right pointing arrow, 3 right pointing arrow, 4 right pointing arrow, head. Real-world use cases, OS round-robin process scheduling, multiplayer game turn management, and carousel/slideshow navigation. We're now in interview territory. Let's tackle 4 classic linked list problems that come up again and again in technical screens. Problem 1. Detect a cycle Floyd's algorithm, also known as the tortoise and hare algorithm. The idea, use 2 pointers. Slow moves 1 step at a time. Fast moves 2 steps at a time. If a cycle exists, fast will eventually lapse slow, and they will meet inside the loop. If there's no cycle, fast will reach none, and we bail out. Click the implementation, initialize both at head. In the while loop, advance slow by 1, and fast by 2. If they are ever the same node, cycle detected, return true. If fast or fast.next hits none, no cycle, return false. On time, O1 space. No hash set needed. Click problem 2, find the middle node. Same 2-pointer trick. When fast reaches the end of the list, slow will be sitting exactly at the middle, because slow has moved half as many steps. For an even length list, this returns the second of the 2 middle nodes. On time, O1 space, 1 pass. Next, problem 3. Merge 2 sorted linked lists. Given 2 sorted linked lists, produce 1 sorted merged list. Click the trick is a dummy node, a sentinel head that lets us avoid special casing the very first node we attach. Cur starts a dummy, and we walk both lists simultaneously. At each step, we pick the smaller value between L1.data and L2.data, attach it, and advance the corresponding pointer. When one list is exhausted, we attach whatever remains of the other. Return dummy.next, skipping the sentinel. On plus M time. Click problem 4. Remove the nth node from the end. This uses a 2-pointer gap technique. We create a dummy node before the head to handle edge cases. We advance fast by exactly n plus 1 steps ahead of slow. Then we move both pointers in tandem until fast hits none. At that point, slow is positioned exactly before the node we want to delete. Execute slow.next equals slow.next.next to remove it. Return dummy.next. Why n plus 1? Because we want slow to stop one node before the target, so we can rewire the pointer. Think of it as leaving 1 extra step of gap. Let's consolidate everything into a complexity table. This is your reference card. Access by index, always ON, for both singly and doubly linked lists. No random access, ever. This is the single biggest drawback compared to arrays. Search ON linear scan. Same for both. Insert at head O1 for both. Just rewire the head pointer. Insert at tail ON for a basic singly LL because of the traversal, but O1 if you maintain a tail pointer. Doubly LL with tail pointer is always O1. Insert at position ON for both. You have to walk to the position. Delete at head O1 for both. Same as head insertion. Delete at tail. Here's the critical difference. ON for singly LL, you need to find the second to last node. O1 for doubly LL, you jump straight to tail, previous. Delete by value ON for both. You need to search first. Reverse ON for both. Space per node. O1, extra overhead. 1 pointer for singly, 2 pointers for doubly. Memorize this table. It will guide you in every data structure decision, and will come up directly in interviews. One practical thing you should know. Python ships with a production quality doubly linked list called collections.dequay. You don't need to roll your own for most real-world work. Click Append Left Inserts at the head O1. Append Inserts at the tail O1. Notice both operations are constant time, thanks to the head and tail pointers. Click Pop Left removes from the head O1. Pop removes from the tail O1. Again, constant time. Click Dequays make great queues. In queue with append, dequeue with pop left perfectly FIFO in O1. Click they also make great stacks. Push with append, pop with pop, LIFO in O1. The key takeaway. Whenever you see a problem that needs O1 insertions and deletions at both ends, reach for collections.dequay. Don't reinvent the wheel. Linked lists aren't just academic exercises. They power real systems you use every day. Click on the OS and Systems side. Round-robin CPU scheduling uses a circular linked list. Virtual memory management uses free list tracking with linked lists. Every time you hit Ctrl+Z in an application, undo and redo is typically managed with a doubly linked list of states. And browser /forward history is a classic doubly LL use case. Click higher level data structures are built on linked lists. Stacks, queues, dequees, and hash table collision chains all use them under the hood. Click in everyday applications. Music players use doubly linked lists for previous/next track. Photo viewers use circular lists for looping slideshows. Text editors, especially those with gap buffers, use linked structures for cursor movement. Graph adjacency lists chain together neighbor nodes using linked lists. Clicking in the Python standard library specifically, collections.deque is a doubly LL, queue.queue wraps it for thread-safe FIFO, and Python's async yo event loop cycles tasks using a circular structure. Next, let's bring everything together in one clean, compact implementation. Click the node class, data, and next, 2 lines. Click linked list, __init__, just the head pointer set to none. Click insert _ at head. Create a node, point its next at the old head, update head. All on one line. Click insert _ at tail. Edge case for empty list, otherwise walk to the end and attach. Click delete, handle empty, handle head match, then walk with 2 pointers and bypass the target node. Click reverse, the 3-pointer dance, previous, current, next. Walk the list flipping each arrow. Click _ repro, __, collect node data, join with arrows, append none. Click the final demo, build a list from 1 to 5, print it, reverse it, print again. 2 lines of code, exercising the entire implementation. This is the kind of clean, interview-ready implementation you'd write on a whiteboard or in a coding screen. Simple, readable, and correct. Next, let's lock in the 8 key takeaways from this video. 1. Linked lists store elements in disconnected nodes connected by pointers. No contiguous memory required. 2. Singly linked lists use a single forward pointer. Simple, low overhead. 3. Doubly linked lists add a backward previous pointer, enabling O1 tail deletion. 4. Circular linked lists close the loop, ideal for cyclic or round-robin scenarios. 5. Head operations are always O1. Tail and middle operations are ON unless you maintain a tail pointer. 6. The 4 must-know interview problems. Floyd's cycle detection. Find the middle, merge 2 sorted lists, and remove the nth node from the end. All 4 use the 2-pointer technique. 7. Python's collections.deque is a battle-tested doubly linked list. Use it in production instead of rolling your own. 8. The general rule. Reach for a linked list when insertion and deletion frequency is high and random access is rare. Otherwise, arrays and lists win. Here's your cheat sheet. The 5 most critical code patterns you need to have at your fingertips. Click Node Definition, Data, and Next. Add Self. Previous if doubly. Click Insert at Head O1. 2 lines. New.next equals head, then head equals new. That's it. Click Insert at Tail ON. Walk while cur.next is not none, then attach. Click Delete by Value, ON. Walk while cur.data equals val, then previous next equals cur.next. Click Reverse in place, ON. The 3-pointer loop. Set previous equals none. Walk, flip each next to previous, advance both. After the loop, head becomes previous. Click Detect Cycle ON. Floyd's algorithm. Slow and fast pointers in a while loop checking for equality. Click Python built-in. When in doubt, from collections import deque. O1, at both ends. Screenshot this slide, save it to your notes, or write it on paper. These patterns come up constantly. Next. And that's a wrap on Python linked lists. We went from 0, understanding what a node is, all the way through singly, doubly, and circular linked lists, classic interview problems, and the full Python implementation. If this was helpful, hit the like button and subscribe so you don't miss the next video in this Python DSA series. Drop any questions in the comments, and I'll get back to you. See you in the next one.